Hi everyone, this is the first session of the Multiple Linear Regression course. This is part of the Applied Statistics in Healthcare series, and I really want to emphasize the applied part because this is something that hopefully will help with the work you're doing, and a big part of how I'm going to do this is to help with things for your routine work. In this first slide we have the syllabus. In the first half, we have in the first 3 weeks we're going to cover important concepts, and those concepts will help you to deal with different situations. And in the last half, in the last 3 weeks, we're going to cover different examples of how to do regressions, and we're going to actually use some of those things that we learned in the concepts to help do a better regression and how to get us out of a situation where we normally might get stuck in. So in week 1, in this first session, we're going to cover the purpose of the course. We're going to give you an introduction to regression. We have a section on regression lines and another section on assumptions. And in our last section, we'll cover diagnostics, which are ways to check our assumptions and deal with any violations to those assumptions. So let's begin. For my purpose of the course, it's to provide supplemental analysis methods for your work. And for the purposes in learning regression, they might be for number 1, help make better decisions faster with an all-in-one approach. Number 2 is to increase accuracy by controlling for other competing causes. And those first two purposes, they're actually related. For example, we may look at age and gender. We might have an opinion about one having a different effect on our outcome. But if we have both of these in the same regression model, that helps us give us more accurate results in a more efficient way, rather than separating data into different gender groups and then slicing that by different age groups, such as 65 and over versus those younger. We can do this all at once, and we can control for competing causes to give each predictor an accurate estimate of its effect on the outcome. For number 3, it's to save resources. We can make better use of the data we already have. We have advanced methods that work well on small samples, like aggregated data, and that's where we began with small samples. So we can use our own data, and that'll save you money. For number 4, it's to develop an expertise in identifying trends. Knowing a regression trend line allows us to better interpret a standard report's results. If you've used trend lines in Excel or Tableau, and especially in SAS or other stat software, you're already doing multiple linear regression. That trend line that comes out of Excel or Tableau, that's the product of a linear regression. So if we do that, if we learn more about multiple linear regression, it's going to help that work as well. Number 5, learn how to risk adjust and do predictive modeling. And they're actually the same thing. With predictive modeling, you might have an extra step with model validation. But whether you're doing risk adjusting or predictive modeling, it's the same regression. And it's the same one that you have in hypothesis testing or effect size measurement. They're all the same. You begin with the same regression and you follow the same steps. Number 6 is to learn concepts that are the foundation of all other regression types. Multiple linear regression was the first regression type, and it set the standard on the things that we look at. We actually have less assumptions of if we're doing a regression correctly, but a lot of the big parts of multiple linear regression get carried over into things like logistic regression or survival analysis. We're all using those same theories of what things are important in calculating those results. Number 7 is to identify group trends useful in telling us if medical centers are improving, getting worse, and if we're all on the path to reaching our goals. So if we do group group differences and trends over time, that would be something we can do all at once in a multiple linear regression. And so we have a motivation for multiple linear regression. This goes back to why the method was created. We'll start with there are two approaches in testing hypotheses. The first is to balance our sample on all important things and then test. And we did that with the COVID vaccine. We balanced our sample, the participants who volunteered for the thing. That was balanced with those who didn't get the vaccine. And number two is to gather data on all important things, then balance mathematically when we test. And that's what we do mostly in our hospital studies. We gather information on things like age, gender, and health status, and then we see what differences being in one intervention might have over traditional KP care. Number one is called an experiment, and the second approach is an observational study. Observational studies always work in healthcare. Experiments with randomization can be impractical or even unethical in healthcare. And the reason is that we might deny care for something that we know works. If you do the experimental study design, then you're going to have a control group and an intervention group or a treatment group. So that control group wouldn't get the service that we may know is helpful to our patients. And the next motivation would be regression allows us to simultaneously test relationships. Otherwise, we'd need to do separate tests. And if we do separate tests, then we increase the chance of making mistakes and saying we're seeing something when we're actually not. Plus, it's not as efficient as doing something all at once. So if we have different things to test, such as is the age effect more important than the gender effect or the health status or disease group that you're in, if we do those separately, that's not going to be as good as looking at all those predictors all at once. And in this last point, it's important to note regression is a robust method that is not sensitive to small or moderate outliers and violations of assumptions. If you have the correct model, your regression estimates will likely be correct given adequate review, especially as your sample size increases. So we have different things that we need to look out for when we do a regression, but these are pretty strong techniques, and it was developed that way. So that was the motivation to give us a better way of looking at things and to get pretty stable results, especially as our sample size gets bigger. And to go back to the idea of doing multiple tests and why we look at a regression that can handle a lot of different questions all at once, we're going to cover advantages over multiple tests. I'll just go to the bottom half, and we see that multiple regression methods can be very powerful because the independent variables can be either continuous or categorical or a combination of both. In the past, you would need to do a correlation separately from a t-test. So if you wanted to compare an outcome between men and women, that would be a t-test, where if you had two continuous variables such as age and length of stay, that would be a correlation. But regression lets you combine both things at once, and so that's a big advantage. This allows us to control or adjust for other things. For example, the intervention has a strong effect even after making all things equal on age. And doing multiple tests also increases our chances of a type 1 error. Stating that a type 1 error is stating a statistically significant difference when there is no difference. And we generally have three reasons for doing regressions. The first is hypothesis testing, and examples of that would be we expect the group that received the intervention will have the lower readmission rate, or we expect the period after the vaccine to have a lower mortality rate, and so on. Those are the hypotheses that we want to test. And the second reason would be effect size estimation. We may want to know how much of an effect the outcome has. For example, what percentage of readmissions is reduced by an intervention? What are the cost savings from an intervention program? So the hypothesis test would tell us that yes, the intervention actually does save money, and if we wanted to do an effect size estimation, that would be we would find out how much money does it save on the average. And the third reason for doing a regression would be predictive modeling. We create predicted scores for individuals to assign care. For example, we may want to predict a patient's chance of survival, length of stay, or a child's lung capacity, and so on. In the team site, we have book and data files. All files are located in the Stats with Steve team, and then in the appendix I have a set of references that for all the things that are listed in there, for all the books, that is, and I included one of the articles I did a while back, and that one shows you an extension of multiple linear regression. So I'll have some examples of things of how regression has expanded and how it can take on new topics. I have a link to the multiple linear regression folder. It's in, you don't see it here, but it will be in this PowerPoint. That will get you to that folder with all that information. Additional information I have in there are the SAS files, and that's for the motor trend example. It has it's a SAS EG file with the program and the data and the code that I use to run the analysis. And I have our data files. I have it's course_data that has all the data that I'm using in this, and those R data sets are listed here. And I have a link to my homemade RShiny app, which is a GUI, and this will allow you to do regressions. You only need to be connected to the regular KP network. So when you log in the morning and you type in your code, that same thing that gets you onto your team server, as long as you're on that, you can use this link to get into that GUI. I have here a list of terms that I'm going to use routinely, such as y and x. Y is the outcome variable. When I say x, I'm referring to a predictor variable or multiple variables. We also call it an explanatory variable or an independent variable. R squared, statistically significant. I have that here, but I also have it in the appendix. So if you're looking at slides further on down, you can get to it faster by going to the bottom. And so let's begin with the introduction. I'll give you an overview and background of regression. Multiple linear regression is also commonly known as ordinary least squares. That least squares actually refers to part of the formula, and what we're trying to do, we're trying to get the smallest error between our regression trend line and the actual data, so that we might have a scatter of actual data and we're trying to put a trend line in there somewhere in the middle that best represents that actual data. So for regression, we're regressing the outcome on one or more predictors. If it's one predictor, we call it a simple linear regression. If we have multiple predictors, that's why we call it a multiple linear regression. And so the linear part refers to a line that best represents the association between the outcome and predictor. So again, we might have a scatter of data in a graph, and we want to put that line in there that best represents it. And so that's what we're doing with linear regression. And we have outcomes. In ordinary least squares, the outcome is continuous. These are variables with many values, and we see that with age, length of stay, birth weight, cost, and so on. We can, for practical purposes, often treat ordinal outcomes as continuous. And in this, we have a display of how that data might look. This is the scatter that I was talking about. On the top left, we see as mother's estriol levels increase, and that's what's on the x-axis on the bottom here. As that increases, the average baby birth weight increases. And so this is a conclusion that we can make from a multiple linear regression. That black line is the trend that we've created, and those dots represent the actual data. So as we see, that trend falls somewhere in the middle of those dots, and that's what we're trying to use to represent that that relationship in the data. And we have y and x listed, and y on the y-axis, that's for the outcome. On the x-axis, that's for our predictor. We graph trend lines, and on the bottom left corner is where both x and y equal 0. And on the right, we have another trend so regression lines can go up and down. It's just however that trend line is however that pattern of data is seen. So here we see that as baby ages get older, so as we go to the right on our x-axis, which is represents age, as baby ages get older, their heart rates slow down. So on the y-axis, we see their heart rates, and we see those values begin to go down as the baby gets older. And so how we're going to describe that upward or downward trend is called a coefficient. We use b or beta to represent that coefficient. So if beta is less than 0, has a negative value, then we would see a negative relationship, and we would see a decrease in that. If it's positive, if beta is greater than 0, then we see on the left that trend go up. In this bottom graph, we see that there is no relationship between birthday and birth weight. In other words, the trend is flat. Here is the first set of data we're going to use for the first few weeks, and it's the motor trend cars from 1973 and 1974. MPG, miles per gallon, that is our outcome, and all of these other variables can be predictors of a car's MPG. And this is what you generally get from a multiple linear regression analysis. You get information on, such as at the top we have the model results. We have an intercept at the top, and that is standard for multiple linear regression. That would be the point on the y-axis, or the outcome when all the other values are 0. So let me just scroll back up. So you notice how that trend line on the top left touches that birth weight y-axis outcome somewhere here on 0, but that would be the intercept where that line touches the y-axis at a value of 0 on the x-axis. So if estriol level is at 0, this is where we'd expect birth weight to be, where that line touches the y-axis. Okay, so that's what the intercept is, and we have coefficients, and those coefficients are used to calculate what a predicted value could be. So it tilts that trend line for us. So we have 3 values that are negative, so that means that relationship we expect it to go downward as we expect the MPG to go downward as we get larger values for cylinders, horsepower, and weight. Those are the 3 predictors. And we get a standard error that shows us about what's that spread, how much variation do we have. We have a t statistic, which is the coefficient divided by the standard error gives us a t statistic, and we use that to determine probability or significance, and that tells us the probability that we're going to be wrong in stating that there is a significant effect. So say for horsepower, it's 0.14. So if we were to state that horsepower is important, then there's about a 14% chance we're going to be wrong on that. So we usually shoot for is a value below 0.05. For weight, we see that's clearly below 0.05, so we'd call weight a significant predictor of MPG. And we get an overall sense of how well this model performs through our R-square. Ranges from 0 to 1. We see that 0.843 is high. That's actually very high. So we say that this has good model performance and suggest a good model. And so we also, in the middle, we have graphs. And so we see that these trends do point downward. Weight on the far end has a very steep curve, so we know that's pretty important. We have a regression formula, MPG equals 38.8 plus, and then we begin to enter in the coefficients, the negative 9.94, also negative 0.01 for horsepower, and negative 3.17. So we would multiply these coefficients by whatever value we get in our cars to get predicted scores. So if horsepower is 200 for one car, then that 200 is multiplied by negative 0.01. And we sum these values up to give us a predicted value. So we see below that R-square that gives us our model performance is in this, on the bottom right, it's our analysis of variance table. And we have two components at the very bottom called our regression and our error. Our R-square is a balance of those two. So you can see how R-square is actually calculated. It's the regression divided by the total amount of, for the partial sum of squares. So 949 divided by 949 plus 176, and that gives you about 0.843. And a significant result on this line indicates that at least one predictor is significant in the model. And another name for ordinary least squares regression is simple or multiple linear regression. I mentioned that before, multiple when we have more than one predictor. A statistical formula calculates the path of a line that gives the least residual sum of squares. In other words, the line falls in a spot between the data points of your predictor and outcome values with the least errors. So that's what that red line represents. Knowing regression will help you identify significant trends by looking at lines and dashboards. For example, if we saw a flat line, we would know that's not significant. In this regression line with a 95% confidence interval, that confidence interval represents the likely range had we many data sets instead of just one. So if we had many data sets, we might say that 95 out of 100 would have regression lines that fall between those two green lines. So we've mentioned residuals, I just want to mention that it's an error or the difference between a predicted score and the actual observed score. So in this graph below, we have a residual listed, and that's that green bar. It's the distance between this data point that's close to about 9, and then we see that regression trend line. That prediction would put it closer to around 6. So the distance between that predicted value of 6 and the actual value of 9, that would make up our residual. Intercepts and slopes are used to draw any line. The intercept and slope are coefficients generated by regression to create your trend. So it gives you the actual values that you would use to create a line that you do in any kind of mathematical operation. So for example, if the intercept equals 5.05 and our beta coefficient for our predictor, that value that we're going to multiply by our actual value, or our actual predictor value. If we have these two values, we can predict that y equals 7.3 when x equals 3, and then that's the value that's circled on the bottom. On the x-axis of our graph, we see that red circle. So when x equals 3, and we use that intercept of 5.05 and the coefficient of 0.75 multiplied by 3, that calculates to 5.05 plus 2.25. that equals 7.3. And that's what we see in this graph here. When our x equals 3, if we run that calculation, it'll predict that our value is 7.3. And the blue lines intersect at the predicted score of 7.3, which is also the average y-score, where the average y-score and the average x-score meet. We can tell how well the line fits the data with r-square. R-square indicates the proportion of variance of the outcomes accounted for by the predictors. The higher the r-square, the more we can explain why values of y differ. A regression is similar to correlation, but also provides coefficients of incremental changes of 1 for continuous variables as well as for each level of categorical predictors, such as low, medium, or high. And then sometimes our predictors are correlated. Multiple variables can be tested simultaneously in a regression, controlling for each variable's impact and the correlation between predictors. We get more accurate results when testing each separately. Figure 5.1, on the left side we see that we have two uncorrelated predictors, and these are the two circles on the bottom. On the top circle is your outcome. So when we have two uncorrelated predictors, we see that their r-square in each is 0.25. So that added together gives us an r-square of 0.50 because they're uncorrelated. On the right side, we have two correlated predictors. This overlap gives us a lower total r-square of 0.25. So even though we have redundant information in our predictors, it's still better to have both predictors in our model. Here are some guidelines on r-square. On top we have Jacob Cohen defines the middle of the range cutoffs for small, medium, and large. R-square is 0.02, 0.13, and 0.26. So if you have something above 0.26, then you know you have a large r-square. But r-square means different things and in different situations. If we want to extrapolate a trend for the so if we want to use something to predict out into the future for maybe an individual patient's results, we'd want to have something more along the range of 0.70. For r-squares at that level, then you know that that should give you somewhat safe predictions for your different patients. However, if you don't have r-square that's at 0.70, you can still make predictions, maybe not for individual patients, but you can see, but that would work well for groups of children with the same characteristics such as pneumonia. So an r-square 0.26 might not work well for predicting individual patient results, but it could work well for different groups of patients, such as those with sepsis, or they might fall in a certain disease group. So an r-square will mean a different thing in a different context. The predictions for individuals wouldn't be helpful, but they could be very helpful for subgroups, such as intervention groups, hospital and diagnosis groups. And for this, I'll discuss research and statistics. Regression wasn't created in the field of research, but it was a natural fit for observational studies. Those are the ones we mostly do in healthcare and hospitals. And this is where we test many things simultaneously, such as age, gender, and health status. It really helps to research an outcome to design a good study. And the best way to get a more powerful model is to research the topic to find the most important predictors. For example, in Dahl and Hill's 1950s study, they linked lung cancer to smoking. The other prevailing theory on the cause was automobile pollution, and so in the article they actually discuss how they got to the point where they thought cigarette smoking was more important to study than automobile pollution. So imagine now developing a lung cancer model without including smoking as a predictor. We also, with multiple linear regression, we also have health economic outcomes. Two outcomes we often consider are length of stay and cost. Both outcomes are usually non-normally distributed. That's because we have special cases of zero cost, or it's positively skewed because some patients have very high cost. We might consider the median as a good descriptor of the outcome. However, we are always interested in the mean from the economic perspective. We can identify high-cost patients or groups, and if you're working with finance, what they're going to want to use is the mean. So that's often what they would ask for. So if you're trying to project cost in a budget or for future work, you would be working with the mean. Models with an R-squared that is too low to predict hospitalization cost or length of stay of individual patients can still accurately estimate the average cost of groups of patients with the same characteristics. And here's a slide on how to work with skewed outcomes. Outliers have a direct impact in the formulas we use in regression. Our goal in OLS is to minimize squared errors. So if you're off by $10,000, it's not a big deal if it's spread over 10 patients at $1,000 each. But if just one patient is an outlier by going over the predicted cost by $10,000, the associated square error is 10 times larger than it would be from 10 patients at that $1,000 difference. So just one outlier can have a big impact on that regression. It can affect your R-square, and it can actually pull that regression line towards it. And so we have various options for dealing with outliers. We can do trimming, which is just dropping cases. You might get the high cases. And top coding. This replaces high outliers with some maximum value. So for example, say we have a case that it's 20,000. If we top code it 10,000, that $20,000 cost gets recoded over to a value of 10,000. This can improve R-squared, but it won't cover the full range of cost values. It won't be as descriptive. The author that I cited this from prefers top coding over trimming because the most expensive cases are usually important. Trimming and top coding can underestimate predicted costs and lead to high observed expected ratios. So if you're working with the observed expected ratio, that could give you higher than expected values. And then another option is Winsorizing, and that drops equal amounts of low and high values. So you would top code on one end and bottom code on the other. We have things that are called log transformations. The outcome is replaced with the natural log with their more normal distribution transform data more closely conform to the assumptions of OLS modeling. There are some drawbacks, such as back transforming it, and I have them listed here. Other options that we can do are general linear models, such as Poisson and ordinal logistic models, or even a quantile regression. But a better approach would be a Cox proportional hazard model. It's highly effective. And it, for example, the second highest cost might be 10,000, and the model would treat the highest cost of 500,000 as a rank of 2 and 1. So it doesn't have the same impact that you see from outliers. You can look at the models having the smallest mean absolute deviation. This is a difference between your observed and predicted Y. You can use that to find a better model for you. And here are steps in regression. The first is the research and study design. The second is data collection. Don't categorize continuous predictors when possible, and get wide distributions if possible, and use well-defined groups. The third step is descriptive statistics. You examine the outcomes by quartiles or categories. Number 4 is variable selection to define the model. You can use the data, and most importantly, you would use clinical expertise. You would use what you know about what's in the data, or what's in research or existing data, or the opinion of experts. Number 5 is you run and assess the model. Number 6 is you do diagnostics and revisions if needed. Number 7, you interpret the results. And number 8, you make recommendations to your client. And here are some regression strategies that can help improve the model. The top, we would say use the literature and clinical expertise to create your models. This helps with omitted variable bias, and that's and inaccurate coefficients due to them representing other correlated variables that are not in the model. For example, if you have smoking in your model, but you don't have drinking, because smoking and drinking can be correlated, whatever drinking effects are out there, because it's not in your model, it would probably lump over to the smoking variable. So sometimes that smoking variable can look more important than it actually is, because it could represent other health behaviors. And another strategy is to limit the number of predictors to the most relevant. This will reduce overfitting. And overfitting is model performance is overinflated due to chance because of too many predictors, and it performs poorly on future data. Another strategy is to relax assumptions when relevant to get more accurate results. You can do that with nonlinearity and additivity. So these are two assumptions in the model, but you can actually relax them to give you a better model fit. Nonlinear effects, interactions, data reduction, and imputation can help improve the accuracy. Interactions don't always replicate in future work, so base it on theory. Control for known risk adjusters like age, gender, health status, comorbidities, patient demographics, attitudes, and so on. And for in this section, we're going to look at regression lines. We're going to help understand trends. For understanding regression lines are based on two primary components: the regression trend and the residuals. And this is in the formula, and we'll look at some graphs to help show that as well. How well we can trust the trend is determined by the ratio of the regression to residual. And so this is actually how we're calculating it. The bigger the ratio of the regression to residual, the more accurate the results. So the more accurate the predictions we get from those results. Generally, a good fitting regression line will have regression components large in absolute value relative to the residual components, whereas the opposite is true for poor fitting regression lines. And here's an example of regression lines and how they could fit. To the right are two examples of how well it fits. The top half represents a perfect fit. We see all the dots on the regression line. This is something that is not expected to occur except on things such as relationship between pounds and kilograms or inches and centimeters, or if you're working with very small samples, you tend to only see that in those cases. The bottom half represents an imperfect fit. We have a variance greater than 0. It's imperfect in the mathematical sense because the data points are scattered around the line. This happens frequently, and the trend line still provides helpful information. And here's another trend line, and this is actually to help show the regression and residual components of this trend line. So here we have one actual value that we're highlighting in the trend, and at the very top it reads representative sample point, and that's the sample point, that's a data point. And we have a trend line that's pointing upwards, and we see the space between the actual data point and the trend line represents the residual component. And you can notice how big that is, that arrow that's pointing up and down. You see how big that is compared to what's called the regression component. So if we wanted to, say we know the average length of stay is 5 days for certain populations, what we could do is give everybody that prediction of 5 days and treat each patient as if they're going to be here for 5 days. So that's what the y-axis would represent. If we give that value of 5 days to everybody, regardless of what value they have on their predictor variables such as age, then that value is going to, we'd have a trend line that will look just like that straight line across y. But because we feel that maybe age might influence our length of stay, we would say that there's some sort of trend associated with that. So that's what that regression component's doing. It's lifting that trend line up, and how close it gets to, or how far it gets away from the actual data point, represents your residual component. So that's the regression and residual components. The regression is moving that trend line from being in a flat position upward or downward. It can go either way. And the distance between that trend and the residual component would be this, what we see in this vertical arrow that's pointing up and down. And on this in this graph, we see a similar situation. We're looking at the trend line. We have an upward trend, and these little stars represent actual data. And this shows us another way of looking at predictive scores. We'll use the formula we derived from the regression analysis to predict y-scores. Y equals a plus b times x, which is our actual value. So when x equals 3, we see that our intercept is at 5.05, which on this y-axis in this graph is right about where that arrow is pointing to, 5.05. And then we have a regression component of 0.75. So we're going to multiply that by 3, which gives us 2.25. So when we have a x value of 3, which we see down here, if we increase our value in x by 3, that should increase our predicted value by 2.25. And that would, when you add these two values, the intercept of where we're starting at, and that increase in that expected increase in our outcome by our value of 3 on our predictor, that should give us a value of 7.3. So we go to 5.05, we go over to a value of 3, and when we go up to 2.25 points, that gives us a value of 7.3. And if we do that for 5, if we multiply our regression coefficient of 0.75 by 5, we should have a 3 points. Our expected increase would be 3.75. So we go to our intercept of 5.05. We go over to the x-axis value of 5. And if we go up 3.75 points, that takes us right here where this where it's marked off on at about 8.8. So that's how we calculate a regression trend line, or how we get the predicted score. And that's what we get from the model, is the intercept and slope. In this part, in multiple regression, we're going to have multiple slopes, so we're going to add these values, more values, to get our predicted score. The slope is the change in y we expect from each increase of 1 in our predictor x. Slopes can increase our predicted score as above. It can increase it as we see in this graph, or decrease it in another data. So in this, we're going to look at what happens when we have 4 regression coefficients that are the same value. It's 0.75, and or I'm sorry, they're not identical, but this shows us how our regression and residual components can impact our model fit. So ideally, you want to have the biggest regression component compared to your residual component. The best fitting regression line is depicted in Figure A, with large regression components and small residual components. We get the best fit. So we see our regression component is bigger than our residual component. And the worst fitting regression line is depicted in figure D on the bottom right, which has a small regression component and a large residual component. So we see that residual on top is a lot bigger than our regression component. So this model is dominated more by error than it is by the regression component. For intermediate situations, we see that in figure B and figure C in the top right and the bottom left. And the way that we quantify that relationship between our regression and our residual components is through R-square. And in this graph, we do actually have 4 regression lines, all of them having a regression coefficient of 0.75. So their regressions are heading in the same direction at the same incline, but we do have 4 different types of model quality. We did have 4 different R-squares, and the reason why is, for example, on the top left we have an R-square of 0.54, and we see that because our regression trend line falls between these actual data points, which are represented by the stars. We see that those data points are actually pretty close to our trend line, and so because of that, that gives us a strong regression component that's bigger than our residual component, and that gives us an R-square of 0.54. So it's the same sort of intensity or same incline in the regression trend line, and we see that same line in B, figure B on the top right, but we see a greater spread in actual data around the trend line, and so what that leaves us with is a smaller R-square of 0.10. So we have bigger residual components because these actual data points are further away from that trend line. And then on the bottom half, we see that Model C has a higher R-square, higher than Model D, because the extreme values of 1 and 5 in this example produce a larger regression component and smaller residuals than Model D's middle values and on the x-axis we see the values of 2, 3, and 4. We see data points at those values. The range for both is the same. We have x ranges from 1 to 5. Figure C has data just on 1 and 5, while figure D has values from 2 through 4. So what that does is it gives us a smaller standard error of the regression coefficient in figure C, and that gives a lower p-value. In other words, more significance. So we want to be aware of the effect outliers that inflates the importance of results. In this slide, we have some examples of the relationship between regression coefficients R-squared and the sum of squares of regression. So the values in the second bullet, 0.70, those are the regression coefficients, and 0.59. Those regression coefficients tell us how intense that increase is, or what the incline is. So it's more steep, the trend's going up at more of a steeper path than it is compared to this other example of where the regression coefficients are 0.2 in both these two predictors. So we have 2 coefficients on the top that are higher in revealing a steeper trend, and on the bottom they're less intense, they're a little bit more flatter, and that gives you higher values of the sum of squares of regression. For the top, we see that it's 101.05, below it's 30.71. So if we have a bigger coefficient or a steeper trend, that would give you a bigger R-square, and that reflects a better model, and actually means the bigger that R-square is, the more reliable it is if you use predicted scores. And because of the formula, the point where the mean of our predictor x and the mean of the outcome y, they meet, they must always be on the regression line. So the mean of x and the mean of y are, where they intersect, will always be on the regression line. So we see that trend lines always include the point where the means of the outcome and the continuous predictor variable intersect. We see that in the red square below. Those green lines represent where the means of our variables are at. They intersect at that red line. That blue trend line is our predicted regression line. The blue dots represent predicted scores. Those hollow circles, those points represent the actual data. So on the far left, we have an actual value of over 25 miles per gallon, and slightly below it is our predicted value. But knowing that the mean of x and the mean of y are going to intersect, and that point will be on the trend line, we can often hand draw regression lines in small samples, knowing that fact. And now we're going to cover assumptions. We consider our conclusions are valid when the regression assumptions are generally met, and we cover how to deal with the violations of assumptions. So we often come across points when our assumptions are violated, but that's not a horrible thing. It's not good, but there are ways to work around that. As I mentioned before, regression is a robust method. So if you have violations to your assumptions, or if you have a lot of outliers or some outliers, then if you have a big enough sample, regression shouldn't have a problem with that. For our OLS assumptions, they are number one, linearity, and that's relationships between the predictor and the outcome variable. This assumption can be relaxed with the use of nonlinear terms, such as our variable might be, we might add the squared term to give us a bend and give us a nonlinear trend. Additivity, the impact of different covariates is additive. In our formula, we define it as y equals a plus b1 plus b2. This assumption can be relaxed by using interactions. And so instead of adding b1 and b2 together, we could multiply b1 and b2. Age and gender is a common interaction. For our third assumption, it's independence. The errors associated with one observation are not correlated with the errors of any other observation. So if my data is in there and I have 5 rows of data just for me, then my observations are now correlated. So that would be a violation of the assumption. Normality, errors are normally distributed. We can observe with histograms. The fifth assumption is the homogeneity of variance, which is also called homoskedasticity. The error variance should be constant across levels x. If not, you have heteroskedasticity. And number 6 is the model specification. The model is specified correctly. This is based on your judgment. In other words, do you have all the right variables in there? And here's some notes on normality and independence assumptions. The normality assumption is most important in small samples and large samples, and an analog to the central limit theorem can be used to establish the unbiasedness of your coefficient B as an estimator of your population estimate, and the appropriateness of tests of significance concerning B, or beta, your coefficient. In other words, the coefficient estimates are more accurate as a sample gets larger. The independence, and for the independence assumption, like I mentioned, if 5 rows of my data are in there, that would be an issue, but we do have ways of dealing with that to help make sure we get appropriate standard errors that are not too small. So assumption 1 is linearity, and this is how we examine linearity. We see a somewhat mostly linear relationship between are miles per gallon and horsepower. These values may suggest a nonlinear fit that may be more reasonable. If so, we can relax the linearity assumption and include a nonlinear fit, which we'll do later. In assumption 2, it's additivity, and that's that equation y equals a plus bx. The model meets the assumption if it's specified that way. There are times when it is better to relax the additivity assumption. For example, you might want to fit an interaction between age and gender, and in your model it'll look something like y equals a plus b1x times b2x. So we'd multiply the two terms rather than adding them together. Assumption 3 is independence, and independence is met if the observations are not correlated with each other, and that could be if I have those 5 rows of data just for me, or if maybe we have them for groups of people. The results are going to be dominated by those those multiple observations of the same person or group. We call that autocorrelation. If there is random sampling, you can assume the independence assumption is met. If not, a common option is to use robust standard errors, or you could double the size of your standard error for your coefficients, or you could set a lower alpha level. So we said something is statistically significant at the 0.05 level, and we can increase the difficulty in that, or the lower probability of that type 1 error by setting your p-value to 0.01 instead of 0.05, and then design effects that Rosner lists. And for his assumption 4, normality, here's how we can assess that. We can use a histogram. These are the residuals, and I got this from Sas, and for these diagnostics and for this motor trend cars data example, I have the code for that in the files. So the Sas histogram lets us visually see the distribution of residuals. This looks mostly normal, so we'll consider the assumption of normality met. Another way to assess normality is with the QQ plot, which shows the quantiles of variables against the quantiles of a normal distribution. We see some non-normality in both tails. However, the difference looks small, and we had a normal-looking histogram in the last slide. Assumption 5 is homoscedasticity. Here we have the model. On the top right, we see a graph with values spread randomly above and below that trend, or that line of 0 for a 0 residual. So that there's no pattern there, so that's a good sign. But we do see a pattern in the bottom 2 graphs, and that would represent that for some things, for some levels of x, maybe that's age or another predictor. For some levels on that, we're getting more accurate predictions or smaller residuals than in other values of x. So that would be a concern. And here's another plot, so we can plot the studentized residuals by the predictive values. We can check if there are trends in the residuals that would suggest we have heteroscedasticity. This looks normal here, so we don't see a pattern. And assumption 6 is the model specification. We can check by asking ourselves, are the correct predictors in the model? We should use theory, research, and clinical expertise to determine what predictors should go in the model. We want to avoid omitted variable bias, which is not including all the important predictors, and we should consider if interactions or a nonlinear term should be included. So here we have diagnostics. We'll check model assumptions and make model revisions. We can identify outliers and influential observations. Some observations, especially in small samples, may unequally influence regression coefficients because of their extreme values in y and or x. Outliers may have impact on linearity and normality assumptions. There are various approaches to identifying outliers, such as examining residuals and studentized residuals. If we examine outliers, we can do it with studentized residuals. We can identify outliers from the studentized residuals. We'll use a cutoff of greater than 2 and less than -2. We examine this data to see if these cases should be kept in the data as well as our own judgment. The residuals don't seem extreme because our low sample size will keep in the cases, plus unique values may provide us more information on what we are studying. For example, on our an overperforming car would be the Toyota Corolla. Their miles per gallon were 33.9, so they had the best MPG, and so at this time the Toyota Corolla had only been around for maybe 5 or 6 years, and it's maybe not surprisingly Toyota's all-time best-selling car. And if you see a graph of their sales since they started selling the Corolla, it just goes straight. It's at a 45-degree angle. It's a really steep incline. It's got a really great trend, and so we can also, our outliers can be on the low end. This Maserati Bora on the bottom line only gets 15 miles per gallon. Another thing we can use to detect outliers would be values that are 1.5 times above or below the interquartile range. We can also examine leverage for influential observations. We can look at leverage to identify observations that have great potential influence on coefficient. A regression line can be over-influenced by a single data point, especially in small samples. This could lead to the wrong regression line, especially if the x and y values are outliers. They could be on the low or high end. Leverage greater than 2k plus 2 divided by n is considered high. K is the number of predictors, n is the number of observations. Here with our one predictor and 32 rows of data, that comes out to 0.125. So we have the Ford Pantera and Maserati Bora that have potentially high values of leverage. We can also examine Cook's D for influential observation. The general cutoff is calculated as being greater than 4 divided by n. Here that comes out to 0.125. So we have high and low values, again, that could be considered influential observations. Another issue is collinearity. High correlations between predictors can negatively affect results. For the predictors of horsepower, engine displacement, and cylinders, the number of cylinders, we see that there is a high correlation between engine displacement and cylinders. It's 0.90. It's a very high correlation. And what we see is that the coefficients are reasonable. And here, in this example, they could be, you can get coefficients, when there's collinearity, you can get coefficients that make no sense because they're so high or so low. In here they look okay, but we do see that all standard errors have increased. Thereby all predictors will be non-significant, even though we know they are significant. So we have the full model here with 3 predictors included, but if we look at 3 separate models, one for each predictor, we can see how the standard error has changed, and even how the coefficients have slightly changed. We can compare how coefficients and test statistics differ in the full model compared to each single predictor separately in the crude model. And this is how we can test for collinearity. We can use a variance inflation factor and tolerance. VIF, variance inflation factor greater than 10 is a cutoff, and a tolerance below 0.10 is a cutoff. And we see engine displacement and engine cylinders show some signs of collinearity. Data reduction should help, and we'll cover that later. And we see on the bottom right the VIF for cylinders and displacement. Engine displacement's a concern. A problem that we have is too many variables measuring the same thing, which is engine size. The number of cylinders and displacement tells us how much fuel flows through a car. They have the highest VIF. Removing either displacement or cylinders should help. And that's it. We'll continue with session 2 next time. Thank you.